Hey guys, tonight on Slumber Expeditions, we journey to a world without borders, a single, sprawling supercontinent where all of life's ancient dramas unfolded under a single, giant sun. We will dive deep into the epic saga of Pangaea, a landmass that contained every future continent nestled together like a planetary jigsaw puzzle. We will explore the violent forces that birthed it, the strange and magnificent creatures that roamed its unified landscapes, and the immense climatic extremes that defined its existence. This is the story of a 100-million-year reign, a testament to our planet's restless, dynamic nature and the foundational stage for the world we know today. Our comprehensive journey will piece together the evidence from ancient rocks, fossilized bones, and subtle magnetic signals locked within the crust, building a portrait of an entire world so alien, yet the very cradle of our own. So before you settle in, if you're finding comfort in these deep time mysteries, please consider liking this video and subscribing to the channel, but only if you genuinely like what we do here. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It's always fascinating to connect with a global community of curious minds who share this fascination with history's greatest enigmas. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's speculative journey together. Close your eyes and let your mind drift back through countless millennia to a time when the map of the world was a singular, breathtaking sight. You are standing on a vast, red-stained plain of rock and dust, under a sky hazy with suspended silicate particles. The air you breathe is rich in oxygen, denser than in our own time, and it fills your lungs with a potent vitality. The ground beneath your feet is not soil as we know it, but a compacted, arid dust, cracked into a million polygonal fragments by the relentless heat of a sun that seems to dominate the heavens. Before you, the landscape stretches to a horizon so impossibly distant it curves with the planet itself, unbroken by any significant mountain range you can see. This is the heart of Pangaea, a place modern geologists would call the supercontinent's arid interior, a location hundreds upon hundreds of miles from the moderating influence of any ocean. The wind that blows across this desolate expanse is a constant, dry whisper, carrying the fine red dust that will one day settle and become the rust-colored sandstone of the American Southwest, the African deserts, and the outback of Australia. In the far distance, a shimmering heat haze dances, a mirage of water in a land where surface water is a fleeting, precious miracle. The silence is profound, broken only by that ceaseless wind and the occasional skittering of a small, scaly creature seeking shelter from the oppressive midday glare. This is not a world built on a human scale. It is a world of geological grandeur and climatic extremity, a testament to the immense power of plate tectonics that has drawn all the land together into one colossal entity. The sheer scale of the emptiness is humbling, a visual and sensory experience of what it means for a continent to be truly super, a single, unified land where a creature could, in theory, walk from what we now call Brazil to what we now call India without ever encountering a sea. The formation of this monolithic world was not a gentle process of continental drift, but a prolonged and violent tectonic collision that spanned tens of millions of years. Imagine, if you will, the ancient precursors of our modern continents, the bulky shield of Gondwana in the south, containing the future South America, Africa, Antarctica, India, and Australia, and the smaller, but still massive, La Russia in the north, which held the kernels of North America, Europe, and parts of Asia. These were not the distinct shapes we recognize on a classroom globe today. They were amorphous, bulky landmasses separated by a shrinking ocean known as the Reich. The relentless conveyor belt of the Earth's mantle was pushing them together, an irresistible force meeting an immovable object on a planetary scale. The continental shelves, the submerged edges of these land masses, were the first to meet, crumpling like the hood of a car in a slow-motion collision. The immense pressure and friction generated heat on an unimaginable scale, melting rock from below and forcing vast plumes of magma upward through the thickening crust. This was the birth of monumental mountain ranges, far larger and more extensive than the Himalayas of today, their peaks likely scraping the stratosphere, creating a continuous spine of highlands that would have a profound impact on the global climate for millions of years. This mountain-building event, known as the Alleghenian, Variscan, and Washita erogenes depending on the location, was the final act of suturing, the planetary stitches that bound Pangaea into a single, coherent whole. The process was geologically messy, creating a complex underworld of faults, folds, and uplifted plateaus that define the initial topography of the supercontinent. As the mountains rose along the sutures of the colliding continents, the interior of the newborn Pangaea began to feel the effects of its own vastness. With the landmass assembled, it created a phenomenon known as continentality, an environmental condition where the center of a large landmass experiences extreme temperature variations and receives very little rainfall. The newly formed central mountains acted as a formidable barrier to weather systems. Moisture-laden winds blowing from the distant oceans would be forced to rise as they encountered these colossal highlands. As the air ascended, it cooled, and its moisture condensed, falling as rain or snow on the windward slopes. By the time these air masses crossed the peaks and descended into the continental interior, they were dry, desiccating winds, capable of sucking the moisture from any living thing in their path. This created a rain-shadow effect on a supercontinental scale, turning the heart of Pangaea into a sprawling, seasonally harsh desert. It was not a sea of rolling sand dunes like the Sahara, though those existed along its fringes. It was more accurately a vast, cold desert in its southern reaches and a scorching hot one in the north, a landscape of bare rock, gravel plains, and ephemeral salt lakes that would appear after a rare thunderstorm only to evaporate completely under the relentless sun days or weeks later. The red color of the sediments that accumulated here, now preserved as the famous New Red Sandstone of Europe and the Newark supergroup of North America, is a direct testament to the oxidizing, arid conditions where iron in the minerals rusted upon exposure to the dry air. The assembly of Pangaea had another profound consequence. It dramatically altered the planet's biodiversity. Before the unification, the separate continents had fostered the evolution of unique and distinct ecosystems. The flora and fauna of Gondwana were different from those of Laurussia, having evolved in isolation for millions of years. As the continents merged, land bridges were established, allowing for the great biotic interchange of the Permian period. For the first time, species from one hemisphere could migrate into the other. This was a time of both opportunity and crisis. Predators from the north encountered unfamiliar prey in the south. Herbivores faced new competitors for the strange vegetation. Some species, finding themselves in a new world without their specialized predators or with an abundance of unexploited resources, thrived and radiated into new forms. Others, less adaptable or outcompete by newly arrived rivals, faced decline and extinction. This biotic intermingling led to a certain homogenization of life across the supercontinent. The unique provincialism of the earlier Carboniferous period gave way to a more uniform, globalized set of species. This was the world that the early therapsids, the mammal-like reptiles, and the archosaurs, the ancestors of crocodiles and dinosaurs, would inherit, a world where a creature could, over generations, spread its range across an entire planet of connected land, from the frigid southern polar regions to the humid equatorial tropics, encountering different climates, but never a saltwater barrier. The very shape of Pangaea, often depicted as a giant sea or a deformed Pac-Man facing east, with the massive Tethys Ocean nestled in its Great Bay, dictated the circulation of the global ocean. With all the continents fused, the Panthalassic Ocean, the ancestor to the modern Pacific, was a truly global sea, uninterrupted by any significant landmass. This allowed for the development of powerful, unimpeded circumpolar currents that circled the globe, much like the Antarctic circumpolar current of today, but on a grander scale. These currents helped to isolate the southern polar region, contributing to the formation of massive ice caps that, during the late Carboniferous and early Permian, extended far from the pole. The Tethys Ocean, by contrast, was a warmer, more enclosed body of water, a tropical seaway that would have functioned like a giant marine incubator, fostering a diverse and unique aquatic life. The collision that formed Pangaea also destroyed the rich, shallow coastal environments that had thrived in the seaways between the formerly separate continents. These shallow seas, which had been home to vast reefs and abundant marine life, were drained or uplifted into the new mountain ranges, leading to a significant loss of marine habitat. This tectonic reorganization of the world's geography set the stage for a series of ecological crises in the marine realm, a prelude to the greater catastrophes that would eventually mark the end of the Permian period. The world was unified, but it was a unity born of violence and stress, a precarious equilibrium that could not, last forever. The sprawling, arid landscapes of Pangaea were not empty. They were dominated by a fauna of such formidable scale and bizarre anatomy that they would seem to be the products of a fever dream if their bones were not there to testify to their reality. This was the age of the therapsids and the archosauromorphs, a time when the evolutionary lines that would lead to mammals and reptiles were still deeply intertwined, experimenting with body plans and ecological roles in a world with little competition from furry or feathered creatures. The most iconic rulers of the late Permian period, the time of Pangaea's maturity, were the therapsids, specifically a group known as the Dinocephalians, whose name translates fittingly to terrible heads. These creatures were characterized by their massive, thickened skulls, often adorned with bizarre bosses, knobs, and ridges of bone. It is believed these cranial adornments were used for interspecies combat, perhaps for dominance or mating rights, with individuals engaging in head-butting or flank-shoving contests reminiscent of modern musk oxen or bighorn sheep, but on a much larger scale. A prime example is Moe's chops, a bulky, barrel-chested herbivore that stood as tall as a large pony, with a skull so heavily built that its vertebrae had to form a tall spine over its shoulders to anchor the immense muscles required to lift and control its head. Its posture was semi-sprawling, a transitional form between the belly-dragging gait of earlier reptiles and the more upright stance that would later evolve in mammals and dinosaurs. Alongside the herbivorous Dinocephalians were their carnivorous cousins, the ankylosaurs. These were the apex predators of their day, true monsters of the Pangaean plains. An ankylosaur, like Ankylosaurus itself, was a colossal creature, reaching lengths of up to 6 meters and weighing perhaps half a ton. Its skull was enormous, long and narrow, and lined with sharp, recurved teeth, including prominent canines, indicating a diet of large, thick-skinned prey. Its limbs were powerful and positioned more directly beneath its body than those of earlier reptiles, suggesting a capacity for powerful, if not particularly swift, movement. Its brain, however, was small relative to its body size, and its behavior was likely driven more by instinct and brute force than by cunning. To imagine the encounter is to picture a scene of primal brutality. An ankylosaur, its bulb casting a long shadow in the low sun of the Pangaean interior, ambushing a slow-moving Moschops at a dwindling waterhole, the struggle a chaotic, dusty explosion of raw power, bone against bone, a testament to an ecosystem where size and strength were the primary currencies of survival. The success of these creatures lay in their advanced physiology. They were among the first land vertebrates to potentially have some degree of control over their internal body temperature, a precursor to warm-bloodedness, and they may have even had a form of primitive hair or whiskers, though no direct fossil evidence for this integument has been found from this early period. While the Dinocephalians represented one powerful lineage, another group of therapsids was quietly evolving traits that would prove to be far more consequential in the long arc of evolutionary history: the Dicynodonts. Their name means two-dog teeth, a reference to the prominent tusks that protruded from their upper jaws in most species, but this simple description belies their incredible diversity and success. Dicynodonts were the most abundant and widespread herbivores of the late Permian, filling ecological niches akin to those of modern sheep, rhinos, and hippos. They were characterized by their beaked jaws, similar to those of a turtle, which they used to efficiently crop tough vegetation. Many species were toothless aside from their tusks, which were likely used for digging up roots, defense, or display. Their bodies were typically barrel-shaped, supported by stout, pillar-like legs, and they ranged in size from small, burrowing creatures no larger than a rat to immense, multi-ton behemoths like Lysawisha, which approached the size of a modern elephant and was one of the largest non-mammalian synapsids to ever live. The success of the Dicynodonts lay in their remarkable adaptability and their highly efficient chewing apparatus, which allowed them to process fibrous plant material in a way that few other herbivores of the time could match. Their fossils are found on every modern continent, a direct result of Pangaea's connectedness, proving that they roamed freely across the entire supercontinent, from the frigid south to the parched interior, adapting to a wide range of environments and becoming a staple food source for the predators of their age. The other major lineage that would eventually come to dominate the world was also present during the Pangaean era: the archosaurs, the ruling reptiles. In the Permian, they were not yet the dominant force they would become in the Triassic. They were a smaller, more modest group, represented by creatures like the proterosuchids. These early archosaurs were long-bodied, semi-aquatic predators, resembling large, slender crocodiles. They likely lurked in the rivers and lakes that threaded through the Pangaean deserts, ambushing smaller vertebrates that came to drink. Their anatomy held the keys to their future success: a more upright posture than typical reptiles, and certain innovations in their ankle and hip joints that would later allow for a more efficient bipedal gait. For the time being, however, they lived in the shadow of the mighty therapsids, occupying niches that the larger, more terrestrial predators may have neglected. This coexistence was a delicate balance, an evolutionary waiting game. The archosaurs possessed a physiology and a skeletal blueprint that was, in many ways, more advanced than that of their therapsid contemporaries, but the world was not yet ready for their ascendancy. They were the heirs apparent, biding their time in the riparian zones and swamps, while the therapsid dynasties ruled the vast, open lands. The plant life that sustained this incredible bestiary was as strange and ancient as the animals themselves. The great coal swamp forests of the earlier Carboniferous period, dominated by giant club mosses, horsetails, and ferns, had largely receded, unable to cope with the increasing aridity and seasonal climate of Pangaea's interior. In their place, a new flora had arisen, one dominated by gymnosperms, the naked seed plants. These included the cycads, which looked like short, stout palm trees with a crown of stiff, fern-like leaves, the ginkgos, with their distinctive, fan-shaped leaves, and most importantly, the conifers. These plants were far better adapted to the dry conditions. They had deep root systems to seek out scarce water, waxy coatings on their leaves or needles to reduce water loss, and they reproduced via seeds that could survive periods of desiccation, unlike the water-dependent spores of the earlier flora. Walking through a Pangaean forest in the humid equatorial regions or along the wetter coastal fringes would have been an eerie experience. The air would be thick with the resinous scent of pine and cypress, but the understory would be open, not choked with dense ferns and shrubs. The trees would have a familiar, yet ancient feel. The ginkgos, a lineage that has remained virtually unchanged, the cycads, looking primordial and sturdy. This was a world of evergreen resilience, a botanical empire built on toughness and efficiency, providing the tough, fibrous fodder that sustained the great dicynodont herds and, in turn, the carnivores that preyed upon them. The stage was set, the players were in place, and for a time, this unique, unified world knew a strange and powerful equilibrium. The climate of Pangaea was not a monolithic, unchanging desert. It was a complex system of extreme contrasts, driven by the simple, inescapable fact of its immense size. This supercontinent acted as a giant thermal capacitor, heating up and cooling down with a ferocity unknown in our more fragmented modern world. Its sheer bulk meant that the moderating influence of the ocean, which absorbs and releases heat slowly, tempering land temperatures, could not penetrate its heart. This resulted in a climate of staggering seasonality, especially in the temperate latitudes. Summers in the continental interior could be blisteringly hot, with temperatures soaring well above what any human could endure for long, while winters, particularly in the southern hemisphere which was oriented over the pole, could be brutally cold, with temperatures plummeting far below freezing. The fossil evidence for this exists in the form of glacial deposits in what is now South Africa, India, and Australia, showing that large parts of southern Pangaea were covered in ice sheets during the early Permian. As the climate warmed slightly into the late Permian, these ice sheets retreated, but the legacy of this glaciation shaped the landscape, leaving behind scoured bedrock, moraines, and vast outwash plains that would become the arid deserts of the interior. The annual cycle was not a gentle transition between spring and autumn, but a violent pendulum swing between two harsh and unforgiving extremes. The rainfall patterns across Pangaea were equally dramatic and were dictated by its geography. The equatorial regions, receiving the most direct and consistent energy from the sun, experienced a powerful convection system. The intense heat caused moisture to evaporate rapidly from the Tethys Ocean and the few remaining shallow seas, rising into the atmosphere to form towering cumulonimbus clouds that would deluge the land with torrential afternoon rains. These tropical belts were likely lush, humid zones, supporting dense forests of cycads and conifers, and teeming with life adapted to a steamy, greenhouse world. North and south of these equatorial tropics lay the vast subtropical high-pressure belts, zones of descending dry air that create the world's great deserts today. On Pangaea, these belts were amplified, creating the most extensive desert system the planet has ever known. This was the realm of the red beds and the dune fields, where rainfall was not just scarce, but wildly unpredictable. A single, violent thunderstorm might drop a year's worth of rain in a few hours, creating flash floods that would carve deep arroyos into the landscape and fill the ephemeral playa lakes, only for the water to vanish into the thirsty ground or evaporate under the sun within days. The rest of the year was a relentless drought. Life here was a specialized gamble, dependent on the ability to conserve water travel great distances, or lie dormant for long periods. The coastlines of Pangaea presented a different world altogether. Here, the influence of the Pantheon and Tethys oceans created more moderate and stable climates. Moist maritime winds provided consistent rainfall, supporting a fringe of coniferous and ginkgo forests that could be hundreds of miles wide in some places, narrowing to a thin ribbon in others. These coastal plains and river deltas were the biodiversity hotspots of the supercontinent. The mix of reliable water, abundant vegetation, and varied habitats, from mangrove-like swamps to sandy beaches and rocky shores, allowed for a greater concentration and diversity of life than in the harsh interior. It was in these environments that the most complex ecosystems thrived. Large amphibians, relics of the earlier Carboniferous, still clung to life in the wet marshes and river systems. A diverse array of fish populated the rivers and coastal waters, from primitive sharks to bony fish. And it was here that the terrestrial fauna was most dense. Great herds of dicynodonts would migrate seasonally between the interior and the coast, following the sporadic rains or seeking relief from the temperature extremes, their paths worn into the landscape over millennia. Predators like the Gorgonopsians, another fearsome group of therapsids with saber-like canines, would shadow these migrations, their success dependent on the constant movement of prey. The coast was the vibrant, life-sustaining artery of the supercontinent, a green and blue border to an immense and formidable brown interior. Beyond the daily and seasonal rhythms, the Earth itself was undergoing profound changes that would leave their mark on the Pangaean world. Volcanic activity, while not as catastrophically concentrated as it would become at the end of the period, was a constant feature. The tectonic pressures that had built the supercontinent's mountains did not cease entirely, they merely shifted. Magma continued to well up from the mantle in places, creating vast igneous provinces through fissure eruptions that would have covered thousands of square miles in successive flows of basalt lava. These events were not the dramatic, cone-building eruptions of volcanoes like Mount St. Helens, but a more insidious, prolonged bleeding of the Earth's interior. They would have released enormous quantities of carbon dioxide and other gases into the atmosphere over thousands of years, contributing to a gradual greenhouse effect. Furthermore, the assembly of Pangaea had a significant impact on sea levels. With so much of the planet's crust occupied by a single, thick continental mass, the ocean basins were deeper and wider, a phenomenon known as thermoeustasy. This caused a global drop in sea level, further exposing the continental shelves and reducing the area of shallow marine habitats. This fall in sea level, known as a regression, is visibly recorded in the rock record around the world, showing a transition from marine limestone to coastal sandstone to terrestrial red beds. This global drawdown of the seas strangled the rich continental shelf ecosystems and expanded the reach of the arid continental deserts, adding another layer of environmental stress to the world of Pangaea. The planet was, in a sense, holding its breath, its systems pushed to their limits by the very geology that had created its singular landmass. As we conclude this first part of our journey into the ancient world of Pangaea, we'd like to extend a special thank you for listening. If you're finding comfort in these explorations of deep time, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It's always fascinating to connect with our global community of curious minds. You can also share which part of the story has captivated you the most so far. It would be wonderful to start a conversation around it. Now, let the mystery of what we've uncovered so far, the vast deserts, the terrible-headed giants, the pulse of an entire world, settle in your mind as we prepare to continue our exploration into the cataclysm that would bring an end to this supercontinental era. Beneath the sun-baked surface of Pangaea, beneath the roots of its colossal mountain ranges and the deep, red sands of its deserts, the Earth's engine was never still. The very forces that had painstakingly assembled the supercontinent over millions of years were already, subtly, beginning the process of its dissolution. The mantle, that vast layer of semi-molten rock upon which the continental plates float, was convecting with immense, slow-moving currents of heat. The concentration of all the world's landmass into one area created a profound thermal imbalance. The continental crust, being less dense and rich in radioactive elements, acts as an insulator, trapping the Earth's internal heat beneath it. Over time, this heat built up, creating a colossal thermal dome under Pangaea. This superheated mantle material began to strain against the underside of the continental plate, weakening it from within. In certain zones of particular fragility, along the old sutures where continents had collided, or in regions stretched thin by the immense weight of the mountains above, the crust began to sag and fracture. This process, known as rifting, is the precursor to continental breakup. It starts not with a dramatic split, but with a long, slow, regional pulling apart, a stretching of the planetary skin that can last for tens of millions of years before the final rupture occurs and new ocean crust is born. The earliest signs of this rifting were not visible as gaping chasms, but as a dramatic upwelling of magma from the stressed and thinning lithosphere. This manifested in the creation of large igneous provinces, lips, some of the most extensive and consequential volcanic events in Earth's history. The most infamous of these, the Siberian Traps, began their protracted eruption near the end of the Permian period. Imagine not a single volcanic peak, but a series of deep, crustal fractures, hundreds of miles long, bleeding lava onto the surface for thousands of years at a time. This was not the explosive volcanism of a Mount Pinatubo, but a effusive, flooding eruption that covered millions of square kilometers of northern Pangaea in layer upon layer of basalt lava. The total volume of rock produced is almost incomprehensible, estimated to be several million cubic kilometers. The eruptions would have been a constant, ominous feature of the landscape for centuries, a flickering, orange glow on the horizon at night, and a perpetual, choking haze of volcanic gases and ash during the day. The lava flows themselves would have sterilized entire ecosystems instantly, but the true global catastrophe was brewing not in the lava, but in invisible gases these eruptions pumped relentlessly into the atmosphere. The cocktail of gases released by the Siberian Traps and other contemporaneous volcanic events was a recipe for planetary upheaval. Vast quantities of carbon dioxide, CO2, were the primary culprit, a powerful greenhouse gas that began to trap the sun's heat with terrifying efficiency. But the eruptions also released sulfur dioxide, which combined with water vapor to form acidic aerosols that reflected sunlight back into space, creating a short-term cooling effect, a volcanic winter that would have devastated plant life. Perhaps even more insidious were the emissions of halogens like chlorine and fluorine, which would have attacked and depleted the protective ozone layer, allowing harmful ultraviolet radiation to reach the Earth's surface. And there is compelling evidence that the magma, as it intruded through layers of sedimentary rock, baked and vaporized enormous deposits of coal, salt, and carbonates, releasing additional bursts of CO2, as well as methane and toxic organohalogens. This multi-pronged atmospheric assault triggered a runaway greenhouse effect. The planet began to feverishly warm, and the delicate climatic systems that had, with all their extremes, sustained Pangaean life, began to spiral out of control. The warming oceans were the next domino to fall in this chain of catastrophe. The deep, cold waters of the Pantheon Ocean had, for eons, acted as a vast reservoir of oxygen, thanks to the global circulation driven by the cold polar waters sinking and flowing along the abyssal plains. As the global temperature rose, this circulation slowed. Warm water is less dense and does not sink as readily, stifling the vertical mixing that oxygenates the deep sea. Simultaneously, the increased rainfall and runoff from the continents, fueled by the enhanced greenhouse hydrologic cycle, washed unprecedented amounts of nutrients into the oceans. This nutrient surge triggered massive blooms of algae and bacteria. When these microscopic organisms died, their decomposition consumed the remaining dissolved oxygen in the water column. The result was widespread ocean anoxia, the spread of deep, oxygen-poor dead zones. These anoxic waters began to well up onto the continental shelves, suffocating virtually all marine life that could not escape to shallower, more oxygenated refuges. The evidence for this is written in the rocks. Deep-sea sediments from this time transition from gray, fossil-rich limestones to black, laminated shales devoid of any fossils except for anaerobic bacteria that thrive in such conditions. The oceans, the cradle of life, were becoming a toxic, suffocating broth. The final, lethal blow in this sequence was ocean acidification. The staggering volumes of CO2 being pumped into the atmosphere did not all remain there. A significant portion dissolved directly into the surface waters of the oceans. Here, it reacted with water to form carbonic acid, steadily lowering the pH of the entire global ocean. This increased acidity had a devastatingly specific target: organisms that built their shells or skeletons out of calcium carbonate. This includes corals, which built the great reefs of the Tethys Ocean, brachiopods, crinoids, and most notably, the intricate, shelled ammonoids and the entire class of trilobites. In more acidic water, the carbonate ions these creatures needed to build and maintain their hard parts become scarce. Their shells would have literally begun to dissolve, or they would have been unable to form them in the first place, leaving them vulnerable and physiologically crippled. The fossil record shows a stark transition at the end of the Permian. Below a certain thin layer of rock, the seafloors are teeming with the diversity of shelly fossils. Above it, in the earliest Triassic rocks, they are virtually absent. The combination of warming, suffocation, and acidification created a tripartite trap for marine life from which there was no escape. The foundation of the entire marine food web was shattered, collapsing upwards through the ecosystem, wiping out predators and prey alike in the most severe extinction event the oceans have ever witnessed. The cataclysm that devastated the oceans did not spare the land. The effects of the volcanic gases and the shifting climate washed over Pangaea like a slow, invisible tide of death. The first and most critical pillar of the terrestrial ecosystem to fail was the plant life. The initial pulses of volcanic sulfur dioxide and associated aerosols would have caused prolonged periods of acid rain, scorching the leaves and needles of the dominant gymnosperm forests. This, combined with the sharp temperature fluctuations and the prolonged darkness from the atmospheric haze, would have severely reduced photosynthesis. Vast swathes of vegetation, particularly the lush forests of the equatorial regions and the coastal fringes, began to die back. The fossil record from this time shows a fungal spike, a sudden, massive abundance of fungal spores in the sediment. Fungi are the planet's great decomposers, and this spike is a clear indicator of a world drowning in dead and dying plant matter. With the primary producers of the ecosystem in collapse, the entire food web began to unravel. The great herds of herbivorous dicynodonts and other plant eaters, their food sources disappearing, faced widespread starvation. their populations crashed, and with them, the foundation of the terrestrial animal biomass crumbled. For the surviving animals, the changing atmosphere itself became a lethal obstacle. The intense volcanic emissions, particularly the methane and CO2, not only warmed the planet, but also likely led to a significant drop in atmospheric oxygen levels. Some models suggest oxygen concentrations may have fallen from around 30% in the early Permian to as low as 12 to 15% at the end of the period. To put this in perspective, the oxygen level at the summit of Mount Everest is about 7%. For large, active land animals, many of which were already pushing the physiological limits of their respiratory systems, this would have been catastrophic. Life at sea level would have felt like life at high altitude. The dense, oxygen-rich air that had perhaps fueled the evolution of such massive, active creatures like the dinocephalians and gorgonopsians was now gone. They would have been perpetually breathless, struggling to fuel their metabolisms in this new, thin air world. This hypoxic stress would have been especially severe in the warm, humid lowlands, as warm air holds less oxygen than cold air, and in the already arid interior, where animals would have been forced to travel even greater distances between dwindling sources of food and water. The structure of Pangaea itself, once a great highway for life, became a death trap during the extinction. There were no isolated continents to act as refuges. A toxic atmosphere, a shifting climate, and collapsing ecosystems could spread across the entire landmass without any significant oceanic barriers to halt their progress. Species that might have survived in an isolated pocket on a separate continent had nowhere to hide. The fossil beds from the Permian-Triassic boundary tell a grim and uniform story across the globe, from South Africa to Russia to Antarctica. The once diverse therapsid fauna was decimated. The entire magnificent lineage of dinocephalians, the terrible heads, vanished completely. The formidable gorgonopsians, with their saber teeth, were wiped out. The diverse and successful dicynodonts were pushed to the brink, with only a handful of small, hardy species managing to survive into the Triassic. It was a wholesale eradication of the established order. The ecosystems that had been dominated by these creatures for millions of years were not just damaged, they were obliterated, their ecological roles left vacant, the stage swept nearly clean of its principal players. In the wake of this devastation, the patterns of survival and death offer fascinating clues. It was not necessarily the biggest or the strongest that survived, but often the smallest, the most generalized, and the most resilient. Small burrowing animals, like the tiny mammal ancestor Thrinaxodon, had a distinct advantage. A burrow provided a buffer against the wild temperature swings outside, a refuge from the acid rain, and a microenvironment where oxygen levels might have been slightly higher and humidity more stable. Similarly, aquatic or semi-aquatic organisms living in rivers and lakes may have found conditions slightly less variable than on land. Generalist feeders, animals that could subsist on a variety of food sources, insects, roots, carrion, had a better chance of finding sustenance than specialized herbivores reliant on specific plants that had gone extinct. This was a world where adaptability trumped power, where a low-profile, energy-conserving lifestyle was the key to persistence. The survivors were the inheritors of a broken world, a planetscape of scorched earth, choked rivers, and empty forests, holding within their genes the future of terrestrial life. The end Permian extinction, often called the Great Dying, was not a single, instantaneous event, but a protracted crisis that unfolded over tens to hundreds of thousands of years, a blink of an eye in geological time, but an eternity for the organisms living through it. By the time the volcanic fury of the Siberian traps began to subside and the planet system slowly, haltingly, began to stabilize. An estimated 70% of terrestrial vertebrate families and a staggering 95% of all marine species had been erased from existence. The silence that fell over Pangaea must have been profound. The bellowing of the dinocephalians was gone. The great migrations of the dicynodont herds were a memory written only in bone, and the shallow seas were silent graveyards of coral and shell. The supercontinent, now a vast, wounded land, stood on the threshold of a new era. The old dynasties were dust, and into the emptied world stepped the survivors, among them a small, unassuming group of animals that had weathered the storm. The archosaurs. The age of the therapsids was over. The stage, swept clean by fire and suffocation, was now set for the rise of the dinosaurs. The earliest Triassic period, the dawn of a new geological era, was a world convalescing from a near-fatal illness. The landscapes of Pangaea were often barren and eroded, the soils thin and unstable without the binding network of roots from complex plant communities. The first plants to recolonize these devastated lands were not the towering conifers or diverse cycads of the late Permian, but a disaster flora dominated by a few hardy, opportunistic species. A humble, ancient plant group known as the lycophytes, specifically a genus called Plurimia, became incredibly widespread. These were not the giant-scale trees of the Carboniferous, but smaller, cactus-like forms with a single, unbranched trunk topped with a tuft of simple leaves and a cone for reproduction. They were pioneers, able to thrive in the poor, toxic soils and the still fluctuating climate. Their global presence in early Triassic rocks is a testament to the ecological vacuum that existed. They spread across the entire supercontinent because there was little competition and because they were among the very few plants capable of surviving in the harsh post-apocalyptic environment. For millions of years, the Pangaean landscape would have been a strange, sparse place, dotted with these singular, sentinel-like plants, a stark and simple botanical world. The animal survivors emerged cautiously into this new world. The therapsids were not completely gone, but their reign was definitively over. The few dicynodonts that made it through, like Lystrosaurus, became, for a short time, some of the most abundant animals on the planet. Lystrosaurus was a pig-sized, stout-bodied herbivore with a pair of stubby tusks and a beak. Its success likely lay in its generalist diet and its probable ability to burrow, traits that had served it well during the extinction. Its fossils are found in astounding abundance on every continent that made up Pangaea, from South Africa to Antarctica to China and India, making it a key index fossil for this time period. It was a biological placeholder, a temporary custodian of the herbivore niche in a world with few other competitors. Alongside it, the first archosaurs began to tentatively diversify. Early forms were still small and crocodile-like, such as Proterosuchus, a long snout, semi-aquatic fish eater that patrolled the riverbanks. But the emptiness of the world presented an unprecedented opportunity. With the large therapsid predators extinct, there was little to check the archosaurs' expansion into new ecological roles. This period of recovery, known as the Triassic explosion, was a time of rapid evolutionary experimentation. The archosaurs, unshackled from competition, began to explore a breathtaking array of body plans and lifestyles. One major lineage, the Crurotarsans, evolved to fill the roles of large predators and armored herbivores, looking remarkably like the dinosaurs that would come later. They included powerful, quadrupedal predators with deep skulls and serrated teeth, as well as heavily armored, tank-like herbivores. Another lineage, the Avemetatarsalia, were experimenting with the more upright posture and, crucially, the potential for bipedalism. It was from this group that the first true dinosaurs would eventually emerge, small, agile, and likely feathered, appearing in the fossil record about 20 to 30 million years after the Great Dying. They were not the dominant giants of the Jurassic yet. They were minor players in a world still dominated by their crocodile-line archosaur cousins and the last holdover therapsids. But they possessed anatomical advantages: a more efficient, upright gait, a complex respiratory system possibly involving air sacs, and potentially higher metabolic rates that would serve them well in the trials to come. Amidst this archosaurian diversification, another survivor of the extinction was quietly evolving in the shadows: the cynodonts, a highly advanced group of therapsids. These were the direct ancestors of mammals. In the early and middle Triassic, they were typically small, shrew-like creatures, probably nocturnal and insectivorous. The selective pressures of the extinction and the new, dangerous world of archosaur predators had driven them to develop key mammalian traits. Their teeth were becoming differentiated into incisors, canines, and molars with complex cusps for processing food efficiently. Their jaw joints were strengthening, and some of the smaller bones in their lower jaw were, over generations, migrating into the middle ear to become the delicate bones that would give mammals their sensitive hearing. They likely had a covering of hair or fur for insulation, allowing for the maintenance of a constant body temperature and enabling activity in the cool of the night, a niche the cold-blooded archosaurs could not easily exploit. While the archosaurs fought for dominance in the daylight world, the cynodonts were laying the neurological and physiological groundwork for an entirely different kind of intelligence and endurance, a legacy that would wait 200 million years for its own moment in the sun. The world of the Middle Triassic was, in many ways, a world of echoes. Pangaea was still whole, a vast, connected land, but its character was changing. The intense aridity of the Permian had given way to a more seasonal and, in places, even monsoonal climate as the Tethys Ocean continued to influence weather patterns. The interior deserts were less extensive, replaced by sprawling scrublands and open forests. The disaster flora of lycophytes was gradually being supplanted by recovering conifers, cycads, and the first bonedidals, a now extinct group of seed plants that would become important later in the Mesozoic. The rivers ran clearer, and the oceans, though still recovering from the anoxic event, were slowly being repopulated by new types of mollusks, a new lineage of corals that would form the first modern-style reefs, and marine reptiles like ichthyosaurs and nothosaurs that were swiftly taking over the apex predator roles vacated by the Permian sharks and fish. The Great Dying had reset the evolutionary clock. The slate of Pangaea, once filled with the unique and magnificent life of the Permian, had been wiped almost clean. Now, new players were writing a different story on that same ancient land, a story that would lead to the Age of Giants, the Age of Dinosaurs, and the eventual, inevitable breaking of the world itself. As we conclude this second part of our journey into the ancient world of Pangaea, we'd like to extend a special thank you for listening. If you're finding comfort in these explorations of Earth's deepest history, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It's always fascinating to connect with our global community of curious minds. You can also share which part of the story has captivated you the most so far. It would be wonderful to start a conversation around it. Now, let the immense scale of this planetary transformation, the fire, the silence, and the first green shoots of recovery settle in your mind as we prepare for the final part of our expedition, which will explore the legacy of the supercontinent and its final, graceful fragmentation. The immense thermal bulge that had formed beneath Pangaea, the very same one that had contributed to the volcanic fury of the Great Dying, continued to exert its slow, inexorable pressure. The supercontinent having reached its maximum compactness, could no longer contain the pent-up energy of the mantle. The process of rifting, which had begun with subtle stretching and the volcanic outpourings of the Siberian traps, now entered a more dramatic and definitive phase. Deep within the Earth's crust, along lines of ancient weakness, the old sutures where continents had first collided, the rock began to fail. These were not sudden, clean breaks, but the gradual development of a series of massive, parallel fault systems. The land itself began to sink along these faults, creating a new kind of topography, a rift valley. This was not a small gorge, but a depression on a continental scale, hundreds of miles long and dozens wide, flanked by high, fault-block mountains. The initial rifts of Pangaea began to form in the late Triassic and early Jurassic, most notably in the region that would eventually become the Central Atlantic Ocean. Imagine a vast, low-lying valley, scarred by volcanic cones and hot springs, its floor a patchwork of lakes and rivers, slowly, imperceptibly, being pulled apart at a rate no faster than the growth of a human fingernail. Within these nascent rift valleys, a new ecosystem began to emerge, one uniquely adapted to this dynamic and often volatile landscape. The downdropped valley floors created catchment areas for water, forming long, narrow lakes that stretched for hundreds of miles. These rift lakes, much like the modern-day Lake Tanganyika in Africa, were deep and often stratified, with oxygen-rich surface waters and anoxic depths. They became crucibles of evolution, isolating populations of fish and aquatic invertebrates and leading to bursts of speciation. The surrounding floodplains, regularly replenished by volcanic ash and sediment from the eroding rift shoulders, were exceptionally fertile. They supported dense gallery forests of conifers, cycads, and ferns, which in turn attracted a new generation of herbivores. This was the world in which the first true dinosaurs, small and agile, began to find their footing, sharing the landscape with the last of the large, non-mammalian cynodonts and a diverse array of crocodiline archosaurs. The rifts were corridors of life, but they were also corridors of change, the very places where the integrity of Pangaea was most visibly failing. The volcanoes that dotted the landscape were a constant reminder of the thin crust and the molten rock churning just below, a testament to the planetary forces that were, piece by piece, dismantling the unified world. The most dramatic evidence of this continental divorce exists not on land, but locked within the basalt of the ocean floor. As the continental crust stretched and thinned, it eventually became so attenuated that it could no longer bear its own weight. At this critical point, the crust ruptured completely, and the underlying mantle, released from the immense pressure, underwent decompression melting. This magma welled up into the newly created void, cooling to form the first slivers of brand new oceanic crust. This process, known as seafloor spreading, is the engine of plate tectonics. The initial split of Pangaea began between what is now North America and Northwest Africa, with the newborn Central Atlantic magmatic province, Camp, flooding the rift with one of the largest basalt flows in Earth's history, a final, volcanic exclamation mark on the end of the Triassic period. Then, as the spreading center established itself, the two continental halves began their slow, stately drift apart. The North Atlantic would begin to open later, unzipping northward from this central rift, while to the east, a similar process was pulling India and Antarctica away from Africa, opening the nascent Indian Ocean. The Tethys Sea, the great equatorial ocean that had nestled in the Bay of Pangaea, began to be consumed, its ancient crust sliding beneath the southern margins of Eurasia as Africa and India moved northward. This fragmentation of Pangaea had an immediate and profound impact on global climate. The single, Monolithic supercontinent, with its extreme continentality, began to be replaced by a world of smaller, more manageable landmasses, each with its own, more moderate climate regime. The creation of new seaways between the separating continents allowed ocean currents to circulate more freely, distributing heat more evenly from the equator to the poles. The powerful circumpolar current that had isolated the South Pole was now interrupted by the northward drift of landmasses like South America and Australia, allowing warmer waters to penetrate the southern high latitudes and contributing to the overall warming of the planet throughout the Jurassic and Cretaceous periods. The great arid deserts of Pangaea's interior began to shrink, replaced by more humid and seasonal climates as moisture-laden winds could now penetrate deeper into the continents. This climatic amelioration created vast new habitats for life. The expansion of warm, shallow seas along the newly formed continental shelves created enormous areas of sun-drenched, tropical marine environment, perfect for the proliferation of new coral reefs and the complex ecosystems they supported. The world was becoming a more varied, more hospitable, and ultimately, a more biologically diverse place. The drifting continents themselves became arcs, carrying their cargo of life into new and isolated environments. This is perhaps the most significant legacy of Pangaea's breakup. As the landmasses separated, populations of plants and animals that had once roamed freely across the supercontinent were suddenly cut off from one another by ever-widening oceanic barriers. A species of dinosaur that lived in what is now Brazil could no longer walk to what is now Morocco. This isolation became the driver of a new, spectacular evolutionary radiation. On each separate continent, lineages began to evolve independently, adapting to their unique local conditions and filling the available ecological niches. This is why the dinosaur faunus of the late Cretaceous in North America, with its iconic Tyrannosaurus and Triceratops, were so different from those in South America, which featured giant titanosaurs and bizarre predators like Carnotaurus. It is also why the mammals of Australia, isolated for tens of millions of years, evolved into the unique marsupial fauna we know today. The breaking of Pangaea did not just change the map, it rewrote the book of life, fostering an explosion of biodiversity that would have been impossible on a single, connected landmass. The unified world had been a stage for a single, global drama. The fragmented world became a planet of countless, simultaneous, and unique evolutionary experiments. These continents are fitted together, the geological structures match with an uncanny precision. Mountain belts, such as the Appalachian Mountains of the eastern United States, line up perfectly with the Caledonian Mountains of Scotland and Norway, and the fold belts of Brazil continue seamlessly into those of West Africa. These are the ancient sutures, the scar tissue from the collisions that built Pangaea, now scattered across the globe, but telling a unified story of a former whole. The fossil record provides a biological testimony to this ancient connection. Fossils of the same non-marine species are found on continents that are now separated by vast oceans. The Permian reptile Mesosaurus, a freshwater animal incapable of crossing an ocean, is found only in eastern South America and southern Africa. The Triassic herbivore Lystrosaurus, that hardy survivor of the Great Dying, has been excavated from rocks in South Africa, India, Antarctica, and China. The Glossopteris flora, a distinctive assemblage of seed ferns that dominated the southern reaches of Pangaea during the Permian, left its fossilized leaves and trunks in South America, Africa, India, Australia, and Antarctica. These organisms could not have evolved independently and identically on separate landmasses, nor could they have swum across thousands of miles of open ocean. Their distribution only makes sense if these continents were once amalgamated into a single landmass where these creatures and plants could roam and spread freely. Their fossils are like tags on a shared piece of luggage, confirming that these now distant lands were once part of the same continental entity. Perhaps the most elegant and conclusive proof comes from the study of paleomagnetism. When volcanic rocks cool from a molten state, tiny magnetic minerals within them, like tiny compass needles, align themselves with the Earth's magnetic field at that time and become permanently locked in that orientation. The Earth's magnetic field has reversed its polarity numerous times throughout history, and these reversals are recorded symmetrically in the oceanic crust on either side of mid-ocean ridges. By measuring the magnetic orientation and the age of these seafloor rocks, scientists can create a precise timeline of how the ocean basins have opened. Furthermore, the ancient magnetic field can reveal a continent's latitude. The inclination, or dip, of the magnetic minerals indicates how far from the equator the rock was when it formed. By studying the paleomagnetic record from different continents, geologists can plot their ancient positions, creating polar wander paths that show how the continents have drifted over time. The paths for South America and Africa, for example, are wildly different for the last 200 million years, but before that, they are identical, tracing a single, shared journey until the moment the central Atlantic began to open. It is a ghostly, magnetic fingerprint of Pangaea's existence and its subsequent fragmentation. The legacy of Pangaea is also written in the distribution of our planet's mineral and fuel resources. The coal deposits of the Carboniferous period, formed from the vast swamp forests that preceded Pangaea's assembly, are found in North America, Europe, and China, all of which were clustered together in the tropical belt of that time. The formation of the supercontinent's great mountain ranges created the conditions for the deposition of mineral-rich sediments and the circulation of hydrothermal fluids that concentrated metals like gold, copper, and tin. The rifting process that broke Pangaea apart was responsible for the formation of massive sedimentary basins that would later become the world's most prolific oil and gas fields, such as those in the North Sea and along the Gulf of Mexico. The initial stretching of the crust created fault traps, and the subsequent flooding of these rifts by the ocean provided the organic material and the sedimentary cover necessary for the formation of petroleum. Even the locations of diamonds, carried up from the mantle in volcanic pipes, are often related to the deep-seated fractures that formed during the supercontinent cycle. Our modern civilization, built on steel, energy, and technology, is in many ways mining the geological legacy of Pangaea, utilizing resources whose placement was determined hundreds of millions of years ago by the assembly and breakup of this singular landmass. This understanding of the supercontinent cycle, the repeated gathering and dispersal of the Earth's landmasses over billion-year timescales, places Pangaea not as a unique event, but as the most recent chapter in a long, planetary rhythm. Geologists have identified evidence for at least two previous supercontinents, Rodinia, which existed about 1 billion years ago, and Nuna, or Columbia, which preceded it. This cycle is driven by the relentless heat engine of the Earth's interior. The formation of a supercontinent insulates the mantle, causing heat to build up until massive mantle plumes rise, doming and weakening the crust from below and initiating rifting. The dispersed continents then drift across the globe, eventually being drawn together again by the subduction of oceanic crust, which pulls the land masses into a new collision, forming the next supercontinent. We are currently in the dispersed phase of a cycle. The Atlantic Ocean is still widening, the Pacific is closing, and the continents are slowly converging. In perhaps 250 million years, a new supercontinent, which some have dubbed Pangaea Proxima or Amasia, is projected to form, likely as the Americas collide with the merged Eurasia and Africa. The Earth is a dynamic, living planet, and the map we know is but a single frame in a very long and ongoing geological film. To contemplate Pangaea is to engage in a profound form of time travel, to stretch the imagination across a chasm of hundreds of millions of years. The ground beneath our feet, which feels so permanent and solid, is in reality a fleeting arrangement, a temporary snapshot in the endless dance of the continents. The mountain ranges we see as eternal are the weathered roots of ancient, Pangaean-scale collisions, their grandeur a fading echo of a more violent youth. The very air we breathe has a different composition now, no longer the dense, oxygen-rich atmosphere that fueled the giants of the Permian. To stand on the red sandstone of the American Southwest or the Karoo Basin of South Africa is to stand on the fossilized soil of the Pangaean interior, to touch the dust that settled on the backs of Moe's chops and the saber-toothed Gorgonopsians. It is a landscape of ghosts, a world that exists now only in stone and in the mind's eye, yet it is the foundational reality upon which our modern world was built. The story of Pangaea and the Great Dying holds a deep, sobering lesson in planetary resilience and fragility. The Earth's systems can withstand immense perturbations. They can recover from catastrophes that erase 95% of life from the oceans. The planet itself is robust, its geology and climate capable of cycling through extremes that are almost beyond our comprehension. Life, too, is tenacious, clinging to existence in burrows and refuges, waiting for the storm to pass before blossoming again in new and unexpected forms. Yet, the story also demonstrates a terrifying fragility. The extinction was not caused by an asteroid impact, but by the planet's own internal processes, a series of interlocking feedback loops that spun out of control. It shows that a change in the composition of the atmosphere, a warming of the oceans, a shift in the chemical balance of the sea, can be as lethal as any extraterrestrial impact. In our current era, as human activity drives rapid increases in atmospheric CO2, acidifying the oceans and altering global climate, the ghost of Pangaea's end offers a silent, stark warning from the deep past. The mechanisms are different, but the potential for a cascade of ecological collapse remains a sobering possibility written in the stone record. Yet, from this cataclysm, there also emerges a narrative of profound hope and continuity. The end of the Permian world was not the end of a story. It was a brutal, planet-wide bottleneck, but through that bottleneck passed the ancestors of every living thing we see around us today. The cynodonts that survived in the shadows gave rise, over an immense span of time, to the entire class of mammals. The archosaurs that seized the day evolved into the magnificent dinosaurs, who ruled the Earth for another 180 million years, and one lineage of which, the theropods, gave rise to the birds that now fill our skies. The breaking apart of Pangaea created the isolated continents that allowed for the evolution of our own primate lineage in Africa. We are here because of Pangaea, because of its formation, its existence, its catastrophic end, and its graceful fragmentation. Every breath we take, every step we take on this planet, is part of a story that began in the steaming, equatorial forests of the supercontinent and was forged in the fire of its demise. We are the products of the greatest crisis life has ever faced, living proof of its stubborn will to persist and evolve. As our slumber expedition draws to a close, let your mind drift back across the vastness of time, from the unified world of red deserts and terrible-headed giants, through the fire and the silence, to the green, fragmented world we know today. The forces that shape Pangaea are still at work. The Atlantic Ocean widens by a few centimeters each year. The Himalayas continue to rise as India rams into Asia. The East African Rift Valley trembles with the birth pangs of a new ocean. The planet is alive, restless, and ever-changing. So, as you rest, Consider the profound connection we share with this deep time. The calcium in your bones was once part of the Permian seas. The oxygen in your lungs is a legacy of the Carboniferous swamps. The very ground you call home is a pilgrim on a slow, geological journey, a piece of a puzzle that is constantly being rearranged. The story of Pangaea is not a closed book. It is a continuing epic, and we, in our brief and brilliant moment, are part of its unfolding narrative. Let this deep time perspective settle over you like a gentle blanket, a reminder of your own place in the vast and beautiful tapestry of Earth's history. The world changes, life endures, and the great, slow pulse of the planet beats on.